4, and this is going to be dielectric function. So last week we discussed magnetic response of the ideal, namely non-interacting Fermi gas associated with either spin, quantized degree of freedom, or orbital quantized degrees of freedom. So as we discussed in details, the magnetism is quantum phenomenon. Today we are going to change gear and discuss interacting fermionic system. In particular, since fermions, namely electrons in the metal, are charged particles, and as charged particles they interact through the long-range Coulomb interaction, we're going to discuss the behavior of the electron system with a Coulomb interaction. And before I proceed with the calculations, let me give some definition of the response function I'm going to deal with, which is in the title of this lecture. And I would like to start with Maxwell equations. In particular, I'm interested in those two Maxwell equations which do not contain magnetic field. I have a function d, so this is Nabla function of d of r t, which is related to the charge, the external charge which you have a system. You know, when you apply electric field to the system, yeah, good morning. There are also charges which induced due to polarization of your system. So I need to separate external and induced charge. So the d function, this is 4 pi e rho density of external charges, r t, and there is so-called E field, which is associated with the total charge r external. Good morning. Okay, these are these two pairs, two Maxwell equations which I need. I take a Fourier transformation of these two electric field induction function. Again, the difference is that the electric field E, or induction of electric field E, is related to the total charge. I explicitly put charge in front, and rho is then the density of particles. Good morning. So the Fourier transform d r t is integral over dq over 2 pi q. Again, integral over d omega over 2 pi e to the power I u r minus omega t times d over q omega. And the same way I define a Fourier transform of the electric field induction. E over RT is the integral over dq over 2 pi cube, integral over d omega over 2 pi e to the power I q r minus omega t e q omega. So I plug in these Fourier transforms into the Maxwell equation, and then they will be part of the dielectric function. Well, let me first plug it in. So from equation number 1, I have I q d over q omega is equal to 4 pi e rho external q omega, and from the second equation I have I q e q omega. Of course, I applied also Fourier transform to the density. It's 4 pi e rho total over q. Okay? So, here, in these equations, I can decompose my electric field as part parallel to the wave vector and perpendicular to the wave vector. So to say, let's say, some vector A would be decomposed as A parallel plus A perpendicular, where parallel and perpendicular is related to the direction of the wave vector. And from now on, I will only be dealing with longitudinal, namely parallel to the wave vector component of the electric induction. Which means I have I q d parallel component. This is projection now to the direction of q vector. Q omega is equal to 4 pi e rho external q omega, and I q e parallel q omega is equal to 4 pi e rho total q. And rho total, as I said, is the sum of rho density associated with external charges plus rho induced charges. So the definition of the dielectric function EQ omega, epsilon over q omega, is the ratio of density of external charges q omega divided by the density of the total charges over q omega. Or if I re-express density of total charges in terms of density of external charges, in terms of density of total and induced, equivalently this is minus rho induced q omega divided by rho total q omega, and based on this definition we will insert probe charges into our fermionic system subject to Coulomb interaction, compute using perturbation theory the density of induced charges, and therefore compute the dielectric function and discuss its properties. So this is a goal for today. Okay? So we'll keep this definition on the blackboard and erase everything else. And the method which we are going to apply is called random phase approximation. It's a very powerful method which I will reintroduce you again when we discuss a magnetic response in the system of localized moments. The most natural way to apply this random phase approximation is to use diagrammatic technique. However, as I said, it's not part of my course. Therefore, I will proceed with a bit old-fashioned method of derivation, which nevertheless will bring me to the same results and the same conclusions. Just a remark for you that there is a much more efficient way to do it, and I encourage you to learn yourself methods of perturbation theory for many body physics. And let's proceed with the calculations. Okay, we have system with some atoms which can be ionized. You know that the metal are crystals. So you have a lattice, you have atoms. In most cases, these atoms have s electrons or p electrons or d electrons, but the inner shell is typically s electrons. They are collectivized, so you have ions which are charged, and therefore, so to say, you have a collective mobile itinerant electrons which are responsible for metallic properties such as possibility to conduct electric current, and there are heavy ions which are sit in the positions of the crystalline lattice. So the density operator of R, we have a point like charges. For the moment I don't care about crystalline lattice. I will only consider that I have a point like charges. Sum over position of these charges, delta function R minus R. So this is the density operator in coordinate space. And what I need to do, I need to second quantize it. In order to do it, I will write it rho R in terms of creation and annihilation operators. So I have some amplitudes k prime, and I have a k sigma, a k prime sigma, and summation is taken over k prime and sigma when the amplitudes a k prime is integral over d A. I have the wave function star A delta R minus RA psi k prime A. So this is a standard notation for the second quantitation amplitude, second quantization amplitude. So psi diagram psi k for non-interacting system are just plane waves which depend on the wave vector. For interacting system, we need to compute it, and we do it using perturbation theory. So this is actually the line for processing with this lecture. I will do yet another second step where I average and compute the expectation value of the density operator. So now, so this depends on R. By the way, the integral with the delta function can be easily computed. So this is psi k dagger R times psi k prime R. So your amplitude depends on R, since the density does. If I take expectation value of the density operator, and again, this is the density of charges because the charge itself is taken as a multiplier, I will average it with respect to the ground state of the fermionic system, and ground state is the thermosphere. Regardless we have interaction or we don't. So I denote this as a ground state, So for most of my lecture, I will be dealing with temperature equal to 0. However, I will comment what happens at final temperature. If I see the average of A dagger K, A K prime, I will see that the only way to get non-zero expectation value, if I have K and K prime equal, so this is then sum over K sigma. Then if K and K prime are equal, otherwise this operator has zero expectation value. So what I have psi K modulus square depending on R times the density K sigma. Times actually the expectation value of AK sigma, AK prime sigma, which is the distribution function for the fermions. In particular, for non-interacting fermions, this is a known Fermi distribution function which we discussed on the first lecture. So the goal is then to compute the wave function, starting with the wave function of non-interacting system, and this is what we are going to do now. Okay, is it clear where I am, what we are doing? Good. I don't need Maxwell equation anymore, but what I will write down is that we start with a psi. I will denote node K. This is a wave function of free non-interacting particles, which depends on RT. In principle, I can also come to the Heisenberg representation of the operator, where we get the time dependence there. Or I can work with a Schrödinger representation where the wave function depends on time explicitly. So the wave function of non-interacting particles, for the sake of this lecture, I will denote volume with the letter omega. This is normalization, and this is I K R minus I epsilon K T divided by H bar. So this is the plane wave. And again, having written down once, I will adopt the system of units H bar equal to 1. Okay. Good. So, the basis of plane waves. So, K is a wave vector, epsilon K is a dispersion. The basis of plane waves forms a complete orthogonal basis, and any function, in particular the wave functions for interacting system, can be written down in terms of complete orthogonal basis. Therefore, for the function psi K R T, which we are looking for, we can write it down as sum over K prime C K prime psi K prime node over RT. Okay? So psi K node then is associated with a Hamiltonian H node, which is H square K square over 2m. So this is, if we write down our Hamiltonian for the system as kinetic energy plus interaction. And we keep in mind that the function psi k satisfies the Schrödinger equation with this Hamiltonian. So I h bar d psi k over dt is equal to h naught plus v psi k. And we plug it into the Schrödinger equation. What we obtain, so this is of course also depending on time, I h bar, so now I have two terms. I have a product of two functions. So then this is sum, well, let me write it this way, sum over k prime. I open bracket here. So this is d ck prime over dt psi k prime node. This is the first term. I will ignore the arguments. Then plus c k prime d psi k node over dt is equal to h node plus v sum over k prime ck prime psi k prime node. Right? However, having written down that, I'm saying that I h bar d psi k node over dt is equal to h node psi k node. So therefore, this term is precisely h node. And I can write down that I h bar sum of the k prime d c k prime over dt psi k prime node is equal to my interacting potential sum over k prime ck prime psi k prime node. So now what I will do, I will take this equation, multiply it from the left hand side to psi k double prime node star and integrate over dr. Okay? So the basis of the wave function, as I said, is complete and orthogonal. Therefore, the integral of the product of these two functions integrated over all r will give me delta k prime k double prime. So I will write this term as h bar d c k prime over dt is equal to, here I have a sum over k prime this is k double prime. I will have matrix element over v k double prime k prime and c k prime, where v k double prime k prime is a matrix element integral over dr psi k double prime star node v psi k prime node. Okay? So far, there are no any approximations. So this is RT, this is RT, and this is RT. No any approximations. However, to solve this equation, we will do it using perturbation theory. We will assume that our interaction is relatively small. We will see a condition for that, and therefore proceed with the time-dependent perturbation theory calculations. Namely, so equation connects us certain wave vector with matrix element of potential taken between this vector and all other vectors. So we will assume that for k double prime equal to k, because we are looking for perturbative correction for the wave function with a given k, so ck is equal to 1. Okay? Which means that in the zeroth order of perturbation theory, for any k double prime or k prime not equal to k, ck is equal to 0. This is a zeroth order in interaction V. In the first order, we can write down that for k double prime not equal to k, from this equation, ck double prime is equal to minus a divided by h, integral from minus infinity to t. So what I do by doing perturbative expansion, I need to plug in here the result of zeroth order perturbation theory. Now, therefore, this is delta function. What I say is that ck prime is delta function kk prime. So therefore, k prime is equal to k, and the sum is gone. So I have a matrix element vk double prime k integral rt prime dt prime. Okay? So this is how I computed the first leading order of perturbation theory with respect to V, assuming that V is small, and as I said, we will write down criteria a bit later. So I'm not going to proceed beyond the first order of perturbation theory, because I'm interested the same way as it was done in computing response to magnetic field in linear response to the theory. And what I do now, I would say that I will engineer this V now. I will say that since it's a probe, kind of probe function, I will introducing some probing potential and computing change of the wave function as a response to this potential. It's quite natural for me to take this potential as a monochromatic function, which is function the only wave vector and the only frequency. So I will say that this is, I will call it external potential, and I engineer it in the form that there is a VQ IQR minus I omega t plus complex conjugated, therefore it's plus VQ star minus IQR plus I omega t. So now, with this form of probe potential, I compute Ck double prime. Okay? So then Ck double prime is equal to minus I over h bar integral from minus infinity to t dt prime. I have Vq sorry, yeah. Now I need to compute the K double prime K matrix element. This is external potential over RT. So matrix element V K double prime K of this potential is equal to integral over dr the wave function which I need to plug in here. This is psi K double prime node over RT, which is 1 over square root of omega e to the power minus a K double prime R plus I e K double prime T. Let me now eliminate h bar from here and there. So now it's too many notations to deal with. So this is psi star K double prime RT. So then I have a potential VQ I QR minus I omega t plus VQ star e to the power I QR plus I omega t. And I have another wave function, omega node, because the matrix element here is computed with the help of non-perturbed wave function. This is I KR minus I AK T. Okay? This is what we have here. Okay, so now the integral over R. So I have this exponent, and this exponent. So integrating over R, this is K minus K double prime plus Q. Right? And 1 over omega is gone. So I have VQ delta function K double prime K plus Q, and the remaining exponent is I epsilon K plus Q T minus omega minus epsilon K T. This is from this term. Now the second term is VQ star. Here I have K double prime minus K double prime minus Q plus K. So K double prime is equal to K minus Q. And exponent I epsilon K minus Q plus omega minus epsilon K T. Okay? So this is star. Sorry. The star is here. Are you with me? Good. So now I plug in this. Okay. I'm doing it in very detailed way, not because it's important, it's very complicated calculations, but because I'm going to make some physical assumption at some moment, and this is precisely the moment. So VQ delta K double prime K plus Q I epsilon K plus Q minus omega plus minus epsilon K T plus VQ delta K double prime K minus Q I epsilon K minus Q plus omega minus AK. So you see, the integral looks very simple. Namely, I'm just integrating to the exponent. The only time dependence is here. However, if you look at my integral with a lower limit equal to minus infinity, I need to tell something what's going on with this oscillating function at minus infinity. Therefore, and this is very important in physical assumption, I assume that my interaction is adiabatically switched on. So the interaction is equal to 0 at very fast and very slowly. So if I will draw the time arrow, the interaction is 0 and then very slowly in time it's switched on. Due to respect this, I will multiply this integral to the multiplier delta t here and there. Actually, I will better. So by the way, this is t prime and this is t prime. I will multiply it to the delta t prime and take a limit delta goes to 0. This is adiabatic turning on the interaction. If I do so, then this integral, where tiny infinitely small additive is added to the exponent, it regularizes the behavior of this function at minus infinity. So in the lower limit, I will anyway get 0. In the upper limit, I get what I get. So this e to the power delta t prime can be written as I minus I delta t prime. Therefore, adding this term means that I can write it minus I delta here and minus I delta there, and this is equivalent way to do it. So I have a function in a complex plane and I regularized it such a way that it behaves properly at minus infinity. So now I can change gear and speed up a little bit. Therefore, Ck double prime is equal to, so this is minus I divided by I, and here I have epsilon k plus q minus omega minus epsilon k vq delta k double prime k plus q and I epsilon k plus q minus omega minus epsilon k t. Minus plus minus I divided by I, the second term, this is star epsilon k minus q plus omega minus epsilon k times vq star times delta k double prime k minus q and exponent I epsilon k minus q plus omega minus epsilon k t. Okay. Good. So just psi k minus q node rt is 1 over square root of volume e to the power I k minus q r minus I epsilon k minus q t, and psi node k plus q over rt is equal to 1 over square root of omega e to the power I k plus q r minus I epsilon k plus q. Okay, so as we said, psi k r t and unit square modulus is equal to sum over k prime c k prime psi k prime node over rt. This is how we expand in terms of the full orthogonal, complete orthogonal basis. So this is exact identity. So now I'm plugging in that. So the first term, when k prime is equal to k and ck is equal to 1, this is psi k node over rt. Now I need to take term with a k prime not equal to k, and therefore this is the delta function. The sign is minus. I have v q e to the power I epsilon k plus q minus omega minus epsilon k t. In this sum, k prime is equal to k plus q, so I have psi at k plus q and divided by epsilon k plus q minus omega minus epsilon k minus vq star e to the power I epsilon k minus q plus omega minus epsilon k t times wave function node at k minus q divided by epsilon k minus q plus omega minus epsilon k plus and so on and so forth. So this k plus q, I would like to take off the wave function psi k node over rt. If I do that, what remains? I will write 1 minus. So here vq. So you see that this I epsilon k plus qt cancels out with this one, right? And epsilon k is taken out of the bracket. So what remains is I q r minus I omega t divided by the denominator epsilon k plus q minus omega minus epsilon k minus vq star, and again I do the same. This is the wave function k minus q cancel out this term and exponent, and what remains e to the power minus I q r plus I omega t divided by another denominator a k minus q plus omega minus epsilon k. Okay? You see that, okay, let's not to be so much in a hurry. Now, if I complex conjugate this wave function, what I need to compute actually psi k r t modulus square. This is psi k r t times psi k star r. So this is psi k r t computed in the lowest order perturbation theory as a response to my probe potential. Okay? If I complex conjugate it, this will be psi node complex conjugated, this will be VQ, an exponent is complex conjugated, and this will be VQ star complex conjugated times exponent. So, and when I start collecting terms, I'm allowed to keep only terms linear in V because I'm in linear response. So what I have is 1 psi k node 1 minus, when I multiply this by 1, this would be VQ I Q R minus I omega t, and I have two terms. One comes epsilon k plus q minus omega minus epsilon k plus 1 over epsilon k minus q plus omega minus epsilon k. The same way minus VQ star minus IQR plus I omega t epsilon k plus q minus omega minus epsilon k plus epsilon k minus q plus omega minus epsilon k. Plus O over V squared. So you see that this multiply in the bracket is the same, and actually I can combine these two terms, and what is here is precisely my probe potential, which I am computing response function to. So 1 is actually density of charges when you don't have any potential. Therefore, all the rest is just a response to the probe potential, and this is induced charge. So I'm back to expression of the density operator over RT. This is sum over K sigma psi K sigma psi K modulus square times NK sigma times Fermi distribution function. So I may write down that rho induced over RT is then minus, I will write it as external potential divided by omega, because modulus psi square is 1 over omega, right? This is 1 over volume times sum over K sigma and K sigma 1 over epsilon K plus Q minus omega minus epsilon K plus 1 over epsilon K minus Q plus omega minus epsilon K. So let me take the first term and denote K plus Q is equal to some K prime. So then K is equal to K prime minus Q. Therefore, if I will write down this term after change of this variable, I will have N k minus q, k prime minus q sigma divided by epsilon k prime minus omega minus epsilon k minus q, k prime minus q, right? And therefore I can take sign minus out of it, so then there will be minus k prime plus omega plus. So it was actually, yeah, okay. And therefore this term is precisely this term, has structure of this term. So this is then minus v external divided by omega, and I have sum over k sigma n k sigma minus n k minus q sigma divided by epsilon k minus q plus omega minus epsilon k. So now let's get this external potential. As I said, I use any probe potential introducing impurity, but let's now compute this potential self-consistently. And in order to do it, we again need to come to Maxwell equation, actually only one Maxwell equation, and proceed with so-called Poisson equation. Because I'm almost done. The only thing I need is properly define this one, self-consistent. I computed it for probe potential, but now I need to plug in real potential. So let me argue that the external is equal to 4 pi e square over q square. Again, this is three-dimensional case times rho external times 1. How one can derive it? So first of all, we write, sorry, this is density of total. So I will replace this external by this potential, and let me argue why it is. So we can write down that V is equal to the charge times some potential, while the electric field is minus gradient of this potential. This is what we get from electrodynamics. So if I write that nabla E is equal to 4 pi E rho tot, this is my Maxwell equation. I can write it down as Laplacian phi is equal to minus 4 pi E rho. This is so-called Poisson equation. And we know how to solve it for point-like charges, if this is a sum of a delta function. So what I do, I will Fourier transform this equation. This will be q squared times phi q is equal to 4 pi e squared rho tot, and therefore phi q, e times phi q, which is vq, is, 4 pi e squared over q squared rho. Okay, so everything is done. I can write down my rho induced here as minus, there is also volume. There is also volume here, and the volume comes, 1 over volume comes here. So I write volume here. Yeah, this is this one. Okay. Good. Rho induced is equal to minus, volume cancel out, 4 pi e square over q square, sum over k sigma, n k sigma minus n k minus q, sigma omega plus epsilon k minus q minus epsilon k. And dielectric function following the definition. Let me take this definition, and there is a rho total here. Dielectric function epsilon q omega, which is 1 minus rho induced divided by rho total. This is 1 plus 4 pi e square over q square, sum over k sigma n k sigma minus n k minus q sigma divided by epsilon omega plus epsilon k minus q minus epsilon k. Good. So, in the remaining part of the lecture, we will see what follows from this dielectric function, what can we learn. So it was kind of formal calculation of the dielectric function, which I did. But now let's discuss properties of this dielectric function. And from the properties of this dielectric function in particular, we are interested in excitations in the system, which we will see are plasmons. And we are interested in static dielectric function, namely screening of the charge. Let me formally write epsilon q omega as 1 minus 4 pi e square over q, some function p q omega, where p q omega is equal to minus sum over k sigma n k sigma minus n k minus q sigma divided by omega plus epsilon k minus q minus epsilon k. So my total potential is V naught q divided by epsilon q omega. This is what this dielectric function is about. So this is V naught, or I can write it as a V naught divided by 1 minus p q omega V naught. If I consider this as a sum of geometric progression, I can write it down as V naught plus V naught p V naught plus V naught p V naught p V naught, and so on and so forth. So this is actually the random phase approximation. I said you that I consider the wave function as just a phase multiplier, and I ignored all correlations between electrons. I did my leading order, first order perturbation theory. So what I got dressed Coulomb interaction, which is given by this. This is random phase approximation, namely all correlation between phases I ignored, and all phases of the wave function considered as uncorrelated, therefore random. property number 1. Let's take limit omega goes to infinity. Okay? So in this situation, this function, which is, by the way, called polarization operator, because it describes the polarizability of the medium because of the charges. So in this limit, p q omega to infinity goes to 0, and dielectric function q omega goes to infinity approaches 1, as it should be. What does it mean? It means that large omega means very short time, and at a short time the system of charges cannot adjust itself to screen the charges. So no screening at short times. Okay. So property number 2. If we take q to infinity limit. Sorry, it's q square, by the way. If we take q equal to infinity limit, then the potential itself goes to 0, which means that the dielectric function is again q to infinity omega goes to 1, which actually means that there is no screening. So potential coincides with the bare potential at short distances. So now we come to tricky properties. Namely, after considering short time scales and short distances, we would like to consider long time scale and long distances. Therefore, we need to take limit q goes to 0 and omega goes to 0. And this is very tricky limit because, as we will see, these limits do not commute. Actually, by assuming one of the limits, namely q goes to 0 and omega goes to 0, you need to specify what goes to 0 first. And this is very typical for fermionic system, for response functions, that one needs to take care about which limits one takes first. For example, let's first the limit no. Let's take the limit that q goes to 0 and omega goes to 0 and q over omega goes to 0. So q goes to 0 faster than omega. So we can write down that epsilon k minus q is equal to epsilon k minus d epsilon k over dk times q. I'm Taylor expanding my dispersion, so this is epsilon k minus velocity, which depends on k, times q for small q. I Taylor expand my dispersion. So nk epsilon k minus q minus epsilon k is therefore equal to minus vk times q. Nk minus q, nk minus nk minus q is equal to nk minus, I Taylor expand the Fermi distribution function, nk plus d nk over d epsilon k times d epsilon k over d k times q, and with a sign minus. So what we have here is plus d nk over d epsilon k times vk. So then I will rewrite it this way. I will write it minus 1 over omega sum over k sigma nk sigma minus nk minus q sigma divided by 1 minus plus epsilon k minus q minus epsilon k divided by. And since I'm a limit q over omega goes to 0, since it's formal, but for the moment, after writing this formal expression, I can take into account that q over omega goes to 0, like this, and I can Taylor expand my denominator. Because the numerator is proportional to q, denominator is proportional to omega, I take omega goes to 0, but this is small. So this is minus 1 over omega, sum over k sigma, nk minus q is equal to d, okay, let me write nk minus q, sigma times 1 minus epsilon k minus q minus epsilon k divided by omega, so on and so forth. So the first term with 1 is equal to 0 because I can shift. The second term gives me, this is minus, plus 1 over omega square, sum over k sigma, nk minus q is d nk over d epsilon k, and epsilon k minus q times v k q. And this is minus then, and I write it square. Let me see that I did not Good. So let me write it this way. Minus p q omega is equal to minus. Now I assume that there is no magnetic field. This is therefore allows me to take a summation of a spin. And this is an integral over dk over 2 pi cube. And I have minus dnk over d epsilon k times v k q square. As I said, I assume that the temperature equal to 0, and let's recall that the Fermi distribution function is a step-like function. So this is my nk, or n energy is a function of energy. The derivative of minus dn energy over d energy is just a delta function at Fermi energy. It will help me to compute. The integral, I come to the spherical coordinate system. This is minus 2 over omega square, integral over 2 pi k square dk divided by 8 pi cube. So I integrate over polar angle. So this is then delta function over epsilon k minus epsilon f. And I have integral over sinus theta d theta. And here I have vk q square times cosine square. This is the scalar product. And the integral is from 0 to pi. This integral can be easily computed as integral from minus 1 to 1 x square dx. It gives me 2/3. So in total, I have minus 2 over omega square times m times 4 pi square, and I have d epsilon k square root over 2m epsilon k, delta function epsilon k minus ef, and I have q square vk square. With your permission, I continue here. So since polarization operator is positive, so this integral tells me that I need to replace epsilon k equal to epsilon Fermi and velocity equal to velocity Fermi. So I have 2/3. So this is cancelled. I have m, I have kf divided by 3 pi square times q square vf square divided by omega square. Let me see that I didn't do any mistake. Yeah. So now I'm plugging it in to the dielectric function. So my dielectric function epsilon k q omega is equal to 1 minus 4 pi e square over q square times this mkf. Let me multiply by m square and delete by m square. I have then kf square kf cube times q square divided by omega square divided by 3 pi square and m square. So if I now cancel 1 over power m, I can write it down that this is 1 minus omega p square plus minus square divided by omega square. The sign is correct because q cancels out in the limit. This is why we needed to take so much care about taking proper limit, what goes to 0 first, where omega plus minus square is equal to, so kf cube over 3 pi square. This is the density of electrons, volume of Fermi sphere. This is 4 pi e square n electrons divided by m. So this is indeed plasmon frequency. Actually, we obtain very important property. Namely, that in the limit q goes to 0, omega goes to 0, q over omega goes to 0, we see that zeros of dielectric function defines the excitations. in the problem. So to say, saying it other way around, epsilon q omega is a response function, because we said that our total draft potential is a zero potential divided by the dielectric function. So to say the response function in the model is inverse dielectric function. So in this limit, it behaves as omega square minus omega plasmon square, and poles of this function, as I say, define elementary excitations in the problem. You probably discussed it with Professor Nersisyan about poles of the response function and so on and so forth. We will see it with magnetic system again, that your magnetic excitations like magnons will also be defined through the poles of susceptibility. Here, the message is that the true response function of the problem electron subject to Coulomb interaction is inverse dielectric function, and its poles define the branch of elementary excitations, which are density fluctuations. The fluctuations of density of charge, these are plasmons. So the plasmons are gapped excitations, namely they are propagated with a certain energy in three-dimensional case. Do the same calculations for two-dimensional case, and you will see, and it's very easy to see it from here. So instead of mass, one needs to plug in tensor of mass. One, you say that the Fermi energy, not a sphere, but kind of cylinder, with a cross-section which is a circle. One of the mass, therefore, you take ellipsoid as approximation, and you send one of the masses equal to infinity. Therefore, the plasmon frequency will be zero for two-dimensional case. But one can go further, compute their next terms, which depend on q. You will get that omega as a function of q square is omega plasmon square plus some coefficient with 3/5 times q vf square. So this is dispersion. And of course, as we did it on a second lecture, by defining some excitations, we also need to care about the inverse lifetime of this excitation. The lifetime should go to infinity. Inverse lifetime should go to zero faster. And in order to do, we should recall that in this equation, there is I delta written here. So your polarization function actually is a complex function. And as any complex function, it has a real part and imaginary part. So the imaginary part, the real part I computed. The imaginary part can also be computed. Your dielectric function is again a complex function. And by computing it, you will find that the decay of these quasi-particles, known as a Landau damping, is exponential for the plasmon branch of excitation. Again, I cannot cover in my lecture everything. Just go and read the literature if you are interested in how to define the lifetime of plasmon excitations. This is given by Landau damping. And the last comment about this limit, because the rest remaining 10 minutes will be devoted to static limit. I would like to ask you to look at this function again, and you see that for omega smaller than plasmon frequency, your dielectric function is negative. The refraction, or say, reflectivity is defined in terms of the square root of the dielectric function, and you see that if dielectric function is negative, square root is purely imaginary, while for omega larger than omega plasmon, dielectric function is positive. Actually, the fact that our metals are so shiny and reflecting light are related to the properties of dielectric function as a function of the frequency. Again, if the frequency of the light is smaller than plasmon frequency, the light is totally reflected, and you see this shiny color of the metals. And why metals look different, why gold has a color of gold and silver has a color of silver, It's just a property of plasmon frequencies of these metals. So this is what actually our story is about. Okay, let's do last exercise and consider the static limit. Limit number 4 is we take omega equal to 0. And while for the limit q equal to 0, omega equal to 0, but q goes first, we need to take some care. In the limit of omega goes to 0, we do it straightforwardly just from very beginning. So this is pi q0 is minus some, let me write minus pi, will be plus sum over k sigma n k minus n k minus q divided by epsilon k minus q minus epsilon k, and I will put factor of 2, assuming that I already proceed with summation of a spin index. Again, this is plus 2. I do the same trick. I will denote k minus q as minus k prime. You can do it again and again, but what I will get is another factor of 2, and this is nk. I have epsilon k minus q minus epsilon k and sum over k. And now, this is minus p is positive, and therefore dielectric function epsilon k 0 is equal to 1 plus 4 pi e squared over q squared, and here there is sum over k, actually times 4, and k epsilon k minus q minus epsilon. Here, let me make a jump. I will ask Jean-Paul to compute you this function. And in order to do it, one needs to integrate over k for three-dimensional electrons with parabolic dispersion. Unfortunately, if I do it now with you, it will take me about 40 minutes. If I will follow all details, I don't have this luxury. I will ask Jean-Paul to do it during the second tutorial. What I will write down is epsilon k0 is 1 plus, epsilon q0. I'm interested in the dielectric function as a function of q, is 1 plus kappa square over q square. This is a result of computation. And here we have 1/2 plus 4kf square minus q square divided by 8kf times logarithm q plus 2kf q minus 2kf. There is so-called 2kf singularity. And kappa square is equal to 6 pi n electron e square divided by Fermi energy. So this is 4 pi e square mpf divided by pi square. So you already recognize the density of states in the Fermi model. If we look at this function, one can write it as dimensional function over q over 2kf. If I denote is as a variable z, this function, which is known and called Linhart function, it's equal to 1/2 1 plus 1 minus z squared over 2z log 1 plus z 1 minus z. This is a Linhart function. If we expand it for small z, z goes to 0. It's now our time to take the limit of small q. We already put omega equal to 0 from very beginning. So what we see that this is 1/2. This is 1 plus 1 minus z squared over 2z. If I expand log, I will get 2z minus 2z cubed over 3. So if I combine terms, I will get 1 minus z squared over 3. So, which means that in the limit q goes to 0, this function goes to some constant. Namely, after taking proper limit epsilon, q goes to 0, omega equal to 0, is equal to 1 plus kappa squared over q squared. So this function diverges at q equal to 0, and it diverges as well over q squared. So dielectric function of metals in static limit goes to infinity, but if we plug in it to the Coulomb interaction, which is v naught divided by epsilon q omega, this is q omega, this is 4p e squared divided by q squared 1 plus kappa squared over q squared. So we see that this is 4p e squared q squared plus kappa squared. So your Coulomb interaction casts the form 4 pi e squared over q squared plus kappa squared. So you see that Fourier transform of this potential does not diverge at small q anymore. So if we take now Fourier transform back to the coordinate space, so v is a function of r, what do we get? We will get you cover potential. This is e squared over r, e to the power minus kappa r. So you see that at small distances, your potential behaves like a Coulomb potential e squared over r, while at large distances it doesn't have long range 1 over r tail anymore, because the tail is exponentially suppressed. So this is your cover potential. If one defined the screening radius or Debye radius as 1 over kappa, then we see at which distances one can get the screening, and one can consider the potential from which distances this screening becomes active. So the last thing I promise you, and let me spend 2 more minutes, is discussion the limit of applicability of perturbation theory. So we did the perturbation theory on a formal basis, but why are we allowed to do that? Or better ask, when do we allowed to do that? And in order to do this estimation, we just need to compare the potential energy and kinetic energy. So we have kinetic energy, which is h squared over mr squared. And we have, for Coulomb interaction, potential energy e squared over r. So what we need to do is to request that potential energy is much smaller compared to average kinetic energy. So which will mean that h squared over m e squared times 1 over r average should be much larger than 1. So this h square over me square is the Bohr radius, right? And the inverse average distance is the Fermi moment. So we come to condition that the electron gas becomes more and more ideal in the very dense limit, because PF is proportional to density, and basically what we have n electron times a Bohr cube is much larger than 1. And this is quite clear, because the potential energy scales is 1 over r, kinetic is 1 over r square. We need to have a dense matter in order to have it more ideal, and this is in very contrast to what we are going to discuss on Wednesday with Bose gas. With the Bose gas, we will consider contact interaction, and of course the range of interaction is just limited by the size, or say, of bosons. But what we need to remember, that all calculations which we did and RPA approximation for fermionic system is applicable in the very dense limit. You may ask me what happens in reality, in real metals. Of course, this inequality can easily be obtained in neutron stars, no problem with that. But in metal, typically, this gas parameter, which is supposed to be much larger than 1, is of the order of 1. It's never much larger than 1. Still, the RPA approximation works quite good qualitatively and quantitatively to describe the behavior of metal, not in thermodynamic, but in a response to electric and magnetic. Okay, any questions? It's tough, you need to digest. I'm pretty sure that this sort of things you didn't discuss on any of your lectures, because it's not part of quantum mechanics and neither part of statistical physics, but we are here to learn something new. Okay. On Wednesday we switch to bosons and proceed with bosons also on Friday. Next Monday at 9 o'clock you will have a first tutorial devoted to computation of the integrals with Fermi distribution function at finite temperatures, which will be given by Jean-Paul Fourier, whom I will introduce you on Friday.